Hey guys, welcome back to my channel, Math Sprint, and you are watching the 7th video of my calculus crash course. Today I'm going to be introducing integration. Now, before we begin, make sure you're familiar with at least these concepts, which will be very important if you want to understand this chapter in calculus. So first, understand these concepts and then continue with this video. The topics to know are basic algebra, polynomials, how to plot a graph on a Cartesian plane, functions and limits, differentiation and its fundamental rules, how to perform differential calculus on different types of functions, implicit differentiation, applications of differentiation, and sigmoid notation. If you want to understand differentiation, you can check out my earlier videos on calculus, which covers these topics. Do note for this video, I'm only working with real numbers and not imaginary numbers. The area under a curve. So early mathematicians were looking for a way to find the area under a graph. Now, when we're talking about the area under a curve or a graph, we mean the area of the region bounded by the curve and some specific set of axes. But there's a problem. The shape encompassed by a curve is rarely a polygon, like a square or a rectangle. If it were a regular polygon, it would be easy to calculate the area. We would just have to use existing formulas like length into width. So how do we find the area under a curve in general? This was the original purpose of integration, also called anti-differentiation. So take a look at the image on the left. The red curve has an equation y is equal to f of x. In this scenario, we want to find the area of the region encompassed by the red curve, the positive x-axis, and the vertical line x is equal to 2, which is shaded in blue. I highlighted this region that I'm talking about in gray here. There are different ways to determine the area of the gray region. I know for a fact that this gray region, it has an area of exactly 4 square units. So we're going to investigate the different ways of approximating areas under a graph without integration. This will go a lot into the topic of Riemann sums. Now, the method mathematicians use to find the area is dividing the region into smaller pieces or strips and then adding them all together. Generally, the width of each piece is equal. We're going to let h be the distance between each of these divisions, and we have a total of n pieces in total. Now, let's suppose we keep increasing the number of pieces. Now, the total area we're calculating is finite and constant. Remember that. So increasing the number of pieces, the number of divisions, causes a decrease in the average width of each piece. So basically, as n approaches infinity, h gets smaller and smaller and approaches 0. There's also something more interesting. The value for the area becomes more and more accurate as the number of pieces increases and the average width of each piece decreases. You'll get to see how this works when I show you Riemann sums. We'll explore the Riemann sums to better understand the integral concept. First, the right Riemann sum. Remember how I told you to divide the region under a curve into smaller pieces? Now imagine those smaller pieces to be rectangles. Here we draw a group of green rectangles whose top right corners lie on the red curve. For this Riemann sum, the top right corner of each green rectangle lies on the red curve. So we have the point x0, y0 on the red curve, also being the top right corner of this green rectangle. We also have the point x1, y1 on the red curve, also being the top right corner of the second green rectangle over here. The same carries forward for x2, y2, x3, y3, and x4, y4, and so on. In fact, since we are using each point on the curve as the top right corner of a rectangle that we draw, that's why it's called a right Riemann sum, or a Riemann sum using right-hand altitudes. The width of each rectangle is delta x0, delta x1, delta x2, and so on, which I indicated at the bottom, just below the positive x-axis. So pretty much the way how this approximation of the area under the curve works is that you just find the total area of all of these green rectangles we formed. We know the area of just one rectangle in general is the length multiplied by the height of the rectangle. So let's find the area of the first rectangle, that is the smallest rectangle. First, we find the width of this rectangle. The answer is delta x0. Then we find the height of this rectangle, which in this case is the y-coordinate of the top right corner of the rectangle. That is y0. So we multiply these two values together. Delta x0 into y0 is the area of this small rectangle. Then we do the same thing for the second rectangle. That is the second tallest rectangle. The width of this rectangle is delta x1. its right-hand altitude, that is its height, is y1. We multiply these two values together, that is delta x1 into y1, to get the area of the second tallest rectangle. Then we do the same thing for the next rectangle. The width of the rectangle is delta x2, its height is y2. We multiply them both together to get the area. And it goes on to the last rectangle that can fit within this region. We sum up all of these individual areas of rectangles to get the approximated area of the region under the curve. Again, remember, this is an approximation. I've shown the formula for the right Riemann sum on the right over here, but since I'm not a big fan of formulas in general, I would advise you guys to just use your head when approximating the area using a right Riemann sum. So what I mean by that is find the width of each rectangle and multiply it with the right-hand altitude. Just remember that in general. But also remember, you have to use the right-hand altitude. That's how this whole thing works. The top right corner point of the rectangle has to lie on the curve. And you have to take the height between the top right corner and the axis lying below it, which in this case is the x-axis. Now I'm going to show you a sample kind of scenario where you need to apply the right Riemann sum. Okay, so here's a sample problem. So we need to approximate the area under a curve with the equation y is equal to x cubed. That is the area of the region bounded by the curve, the positive x-axis, and the line, the vertical line, x is equal to 2. The problem requires us to use a right Riemann sum with a step size of 0.5. So when a problem states a step size, it will likely mean that the width of each rectangle or piece needs to be a particular value. So the width of each rectangle that we draw has to be that specific value, in this case, 0.5. So think of it that our first step is to find all the multiples of 0.5 till we reach x is equal to 2. So those multiples of this case are 0.5, 1, 1.5, and 2. These are the x coordinates of the top right corners of each of the rectangles that we're going to draw. So we plug in these values into the function. F of x is equal to x cubed. So f of 1 by 2 is 1 by 8. F of 1 is 1. F of 1.5 is 27 by 8. F of 2 is 8. So we have to draw the rectangles accordingly, with the help of their top right corners. So for the smallest rectangle, its top right corner should be at the point 1 by 2, comma 1 by 8. The top right corner of the second rectangle should be at the point 1, comma 1. The top right corner of the third rectangle should be at the point 3 by 2, comma 27 by 8. And the top right corner of the fourth rectangle, which is in this case the tallest rectangle, should be at the point 2, comma 8. Remember, as always, for right Riemann sums, the top right corner of the rectangles must lie on the curve. So we sum up the areas of all of these smaller rectangles. You just find the area of each rectangle using the area of rectangle formula. So the area of the first rectangle, the smallest one over here, is 0.0625. And for the second tallest rectangle, its area is 0.5. The area of the third rectangle is 1.6875. The area of the fourth rectangle is 4. You add up all of these areas and you get 6.25, as I showed on the right. But here's something important to know. This is an overestimate. You see that because the total area occupied by the rectangles is greater than the area occupied by the region we're measuring. A general rule that you should know. You can understand this idea if you just view it graphically. When a function is increasing, the right Riemann sum is always an overestimate of the actual area. But when a function is decreasing, the right Riemann sum is an underestimate of the area under the curve. You can take that as like a thumb rule. Now, the left Riemann sum. It's basically the same idea as the right Riemann sum, but instead we draw a group of rectangles whose top left corners lie on the red curve. For this Riemann sum, the top left corner of each green rectangle lies on the red curve. So we have the point x0, y0 on the red curve also being the top left corner point of the green rectangle that I've drawn. We also have the point x1, y1 on the red curve being the top left corner of the green rectangle, the second tallest green rectangle. The same carries forward for x2, comma y2, x3, comma y3, x4, comma y4, and so on. In fact, because we're using each point on the curve at the top left corner of a rectangle, that's why it's called a left Riemann sum or a Riemann sum using left-hand altitudes, as you must have figured out. Again, remember, this is also an approximation. I've shown the formula for the left Riemann sum on the right over here, But again, I mentioned this before, I'm not a big fan of formulas in general, so I would advise you guys to just understand the concept to approximate the area using a left Riemann sum. So what you need to do is you need to find the area of each rectangle and multiply it with its left hand altitude, that is its left hand height. Remember, you have to use the left hand altitude. That is how this whole thing works. It's very important to remember. You shouldn't get confused. The top left corner point of the rectangle that you draw must lie on the curve. And you have to take the height between the top left corner of each rectangle and the axis lying below it, which in this case is the x-axis. Now I'm going to show you a sample kind of scenario where you need to apply the left Riemann sum. Here is a sample scenario. So we need to approximate the area under a curve with the equation y is equal to x cubed. That is the area of the region bounded by the curve, the positive x-axis, and the line x is equal to 2. The problem requires us to use a left Riemann sum with a step size of 0.5. So remember what I told you earlier. When the problem states a step size, it means the width of each rectangle needs to be a particular value, the same value always. So it's the same idea with those multiples of 0.5 till we reach x is equal to 2. So those multiples are 0.5, 1, and 1.5. These are the x coordinates of the top left corners of each rectangle, each of our rectangles. So we plug in these values into the function f of x is equal to x cubed. F of 0.5 is equal to 1 by 8. F of 1 is equal to 1. F of 1.5 is equal to 27 by 8. Now you might be wondering right now, why am I not taking x is equal to 2 like how I did for the right Riemann sum? Well, remember this is a Riemann sum with left hand altitudes. So if I use x is equal to 2, I'll actually end up exceeding the domain, which is 0, 2. Just visualize it. This green line here represents x is equal to 2. If we create another rectangle, its width will be outside the domain, which we cannot allow. So we don't create a left-hand rectangle at x is equal to 2. So we only have 3 rectangles here. We find the areas of each one. You multiply the width into the height to get the area of each rectangle. You can see it on the right over here. You get the area of the first rectangle, that is the shortest rectangle, by multiplying the width 0.5 into the height 0.125. That gets us 0.0625. Then you create the area, you find the area of the second rectangle that you create. It's by multiplying the width, 0.5 again, into its height, 1. So we get 0.5 as its area. Then for the third rectangle, we get its area by multiplying its width, 0.5, into its height, 3.375. That gets us 1.6875. You add them all together and you get an approximate area of 2.25. However, remember in this case, it gives the left Riemann sum is giving an underestimate of the area under the curve. This is because the total area of the rectangles is clearly less than the area under the curve, which we're trying to find. Another general rule that you should know, you can understand this idea again if you visualize it graphically. When a function is increasing, the left Riemann sum is an underestimate of the area. When a function is decreasing, the left Riemann sum is an overestimate of the area under the curve. This rule is kind of like the opposite for the rule of the right Riemann sum. Now for the third Riemann sum, the midpoint sum. It's the same idea with rectangles, but instead of using the top left corner or the top right corner, we're using the top midpoint. Just remember the definition of a midpoint. The midpoint is just a point equidistant from 2 or more points. Here we take the midpoint of the top left corner of a rectangle and the midpoint of the top right corner of a rectangle. The key argument here is that in each rectangle we draw, we must have this midpoint lying on the curve. So look at the diagram on the left. Basically, we draw very wide rectangles. For example, the shortest rectangle that we have here exists on the domain x1, x2, which I'm indicating over here. So the x-coordinate of this midpoint is x1 plus x2 divided by 2. We plug this into the function to get the y-coordinate f of x1 plus x2 divided by 2. We know that the width of this rectangle is delta x2. As you can see, I indicated it. We multiply the width by the height of the rectangle. That is, we multiply delta x2 with the f of x1 plus x2 divided by 2 to get the area of this large rectangle here. We do the same things with the rectangles whose widths are delta x1 and delta x3. Then we sum up the areas of all of these large rectangles to get the approximate area. So let's work with an example. We need to approximate the area under the curve with the equation y is equal to x cubed using a midpoint sum. So we know that the step size mentioned in the question is 0.5. So the width of each rectangle that we form has to be 0.5 again. But here, you have to get the same idea with the multiples of 0.5. We have 0.5, 1, 1.5, and 2. So now we got to get the midpoint values between them. So the midpoint of 0 and 0.5 is 0.25. The midpoint of 0, 0.5 and 1 is 0.75. This is also an average if you think about it. The midpoint of 1 and 1.5 is 1.25. The midpoint of 1.5 and 2 is 1.75. So now we find the x and y coordinates accordingly. F of 0.25 is 0.016. F of 0.75 is 0.42. F of 1.25 is 1.95. F of 1.75 is 5.36. These are the heights of the four rectangles. We find the areas by multiplying the widths and heights and sum up all these areas. We finally obtain an approximate area of 3.875. Notice how this approximation is a lot closer to our exact area of 4. The approximations when we used right Riemann sum and left Riemann sum were a lot different compared to the actual area. But on the other hand, this midpoint sum that we use seems to be a better approximation for the area under a curve. Okay, the final Riemann sum is the trapezoidal sum. In simple forms, instead of using rectangles for this Riemann sum, you have to use trapezoids, also called trapeziums. Now recall the formula for the area of a trapezoid. It is half multiplied by the perpendicular height of the trapezoid multiplied by the sum of the lengths of the parallel sides. There is really no such thing as a right trapezoidal sum or a left trapezoidal sum. So what you do basically is you connect the points you are using together. Each line segment is the fourth side of the trapezoid that is not perpendicular to any adjacent sides or parallel to its opposite side. So you use these line segments to form multiple trapeziums. You can see on the left all the green trapeziums I have drawn. So you just find the areas of each of these trapeziums and then add them together. Okay, so let's work with an example. We know the step size mentioned in the question is 0.5. So the width of or length of each trapezoid we form is 0.5. When I'm talking about the width here, in this case, I am referring to the length of the side of the trapezoid, which is perpendicular to its adjacent sides, but not parallel to its opposite side. So again, we think about the multiples of 0.5. These multiples of 0.5 are 0.5, 1, 1.5, and 2. We find the corresponding y coordinates by plugging these x values into the function. For this problem specifically, you may notice that the first green trapezoid is actually not a trapezoid. It's really just a right triangle. But it won't matter because one of those parallel sides will just have a value of 0, so it won't affect our result. So after summing all the areas, we end up with an approximate area of 4.25. This is, if you notice, the trapezoidal sum is also a very reliable way of approximating the area under a curve. So I want you to recall left Riemann sums and right Riemann sums here. Take a look. Maybe you want to pause the video and draw a rough sketch of their general graphical appearance. Right now, I'm only showing the left and right Riemann sums for increasing functions just for simplicity for now. So now we're going to come to the definite integral. Now you can understand the definition and reasoning behind this. So mathematicians were considering this idea of dividing the region under a curve into smaller pieces in order to find the area under it. Now, a curve with the equation y is equal to f of x, consider it. Since we are trying to find the area of the region bounded by the curve, the x-axis and the domain x's between a and b, inclusive of both a and b, we divide the interval x's between a and b into n subintervals of equal width, and this width will be b minus a divided by n. Well, n is the number of pieces, and a comma b is the domain. We'll let the area under the curve over the interval x's between a and b be capital A. Now consider the left Riemann sum area, which is we're denoting by capital A L, and the right Riemann sum area, which we're denoting by capital A R for the curve. By the way, in case you don't know, when we say consider in mathematics, it doesn't mean think about, it means think about or imagine or take a particular scenario. So here, think about a left Riemann sum AL and the right Riemann sum AR for the curve. Now, if you haven't figured it out already, there's a general formula for the left Riemann sum and right Riemann sum, which I've shown here. AL, for the left Riemann sum, it's AL is equal to B minus A divided by N, multiplied by the summation of f of xi from I is equal to 0 all the way to I is equal to N minus 1. You should recall sigmoid notation here. Now for AR, the right Riemann sum, it's AR is equal to B minus A divided by N, multiplied by the summation of f of xi from I is equal to 1 to I is equal to N. Now, I want you to consider AR minus AL. That is the right Riemann sum minus the left Riemann sum. So if you notice, actually, when we consider this, a lot of these terms actually cancel out. So like f of x1, f of x2, f of x3, and so on, till f of x minus n minus 1, these all cancel out. This means that AR minus AL, the right Riemann sum minus the left Riemann sum in general, is equal to b minus a divided by n multiplied by f of xn minus f of x naught. Now here's the thing. We know that the domain is a comma b. So x naught, which is the smallest value in the domain, is just a. Xn, which is the largest value in the domain, is just b. So the right Riemann sum minus the left Riemann sum, that is AR minus AL, is equal to b minus a divided by n times multiplied by f of b minus f of a. Now consider limits. By the way, if you don't understand limits, you can check out my first video on this calculus crash course. That's the only way you can comprehend grasp the following ideas. Suppose we start increasing the value of n. N starts to become a very large number approaching infinity. What this means graphically is that we are dividing the region whose area we're trying to find into a very large number of rectangular strips or pieces, to the point where the number of strips is infinite. Now recall the idea I brought up earlier. When we are dividing the region into more and more rectangular pieces, we are not changing the area of the region at all. The area is finite no matter what. But when we increase the number of rectangular pieces, the size of each rectangular section decreases. That is, they get narrower and narrower and occupy less space, to the point where the width of each rectangle becomes negligible, even though it still has height. I will be showing you how this looks later. Now, as n approaches infinity, the right Riemann sum minus the left Riemann sum, that is AR minus AL, approaches 0. This is because generally, as you may be aware from limits, the limit of 1 by n as n approaches infinity is equal to 0. And since we know that the actual area has to be between one of the Riemann sums, that is, the actual area can be between the left Riemann sum and the right Riemann sum, or the actual area could be greater than the right Riemann sum but less than the left Riemann sum, because we don't know whether the function is increasing or decreasing. This is a general scenario, but we know one of these cases has to be true. So it follows from this that either way, the limit of the right Riemann sum as n approaches infinity is equal to the limit as of the left Riemann sum as n approaches infinity is equal to the actual area of the region under the curve. So I'll explain how this last part works a little bit more with the diagram. Okay, so take a look at this diagram properly now. The value of h represents the width of each rectangular piece. So as we keep increasing the number of rectangular sections, that is, we increase the value of n from the number of divisions you see on the left, and we increase the number of divisions as shown on the right, and n becomes very large. As n increases, h decreases and starts to approach 0. You can see that from the left image, when we have a smaller value of n, h is larger. But when on the right image, when we have a larger value of n, h is smaller. So as h decreases and approaches 0, and the better part is the approximation of the area becomes more and more accurate. So suppose we have some curve that's concave down and increasing. We use a right Riemann sum to approximate it. When we only use 3 rectangles, as shown on the left, it looks like the approximation is far larger than the actual value. Just look at the diagram on the left. I mean, the combined area of all of these green rectangles is bigger than the area under the red curve. But let's say we increase the number of rectangles to say 15 or something even larger, like 100,000. The width of each rectangle decreases from delta x, as shown on the left, which is a relatively higher value, to a relatively more negligible value of dx. Notice how on the right, the combined area of the rectangles is a lot closer to the area of the region. The rectangles don't occupy as much extra space on the graph on the right. This is the central focus of the definite integral idea. If you take an infinite number of rectangular strips of negligible width and add them together, you get the exact value for the area they occupy. Okay, so now the definite integral, the definition. The symbol that looks like a narrow S is called the integral sign. We use it to denote an integral. So this integral of f of x dx over the domain a comma b is the integral of f of x with respect to x over the interval a comma b on the domain. This integral is equivalent to the area under the curve over the interval a comma b on the domain. Now look at the diagram on the left. Imagine that we are just adding up small pieces of negligible width dx together to get the area of the region. The area of each rectangular strip is width dx multiplied by the height f of x. Okay, so here's a vocabulary check. The word integration means to put together to a whole. So it refers to the process. And integral is the sum or whole produced by the process of integration. Okay, so now anti-differentiation. We know that the process of obtaining dy by dx from y, or f dash of x from f of x, is called differentiation. The opposite process, or the process of finding y from dy by dx, or f of x from f dash of x, is called anti-differentiation. It is the reverse process of differentiation. Now, if you're a bit confused, take a look at the diagram on the right. We perform differentiation on a function f of x to obtain a derivative function f dash of x. If we perform anti-differentiation on a derivative function f dash of x, we obtain the original function f of x. We can say that the derivative of f of x is f dash of x, but the antiderivative of f dash of x is f of x. Now here's the main point. Anti-differentiation is basically just integration. They're essentially synonymous with each other, but the terms are used in different contexts. But they do essentially refer to the same process. Okay, so let's do some problems. I want you to find the antiderivatives of each of the following. Pause the video now and try them yourself. Take about 3 minutes maybe, but do note that when I explain the fundamental rules of integration, you should be able to do this in much less time and with less effort. By the way, you'll still need knowledge of differentiation and algebraic manipulation here, so before solving these problems, you might want to check out my previous videos for this calculus crash course on differentiation. All right, here are the answers. Part A, let's solve it. So we have to find the antiderivative of x to the power of 4. So let's consider we find that the answer to this is 1 by 5 x to the power of 5. We know this because if we differentiate 1 by 5 x to the power of 5, we will obtain x to the power of 4. So when we perform anti-differentiation on x to the power of 4, we obtain 1 by 5 x to the power of 5. But if you prefer like a more algebra-based answer, then let's start with considering d by dx of x to the power of 5. So we know that the derivative of x to the power of 5 with respect to x is 5x to the power of 4. We divide the left-hand side and the right-hand sides of the equation by 5. 1 by 5 is a constant, so the derivative of 1 by 5 x to the power of 5 is x to the power of 4. Okay, so part B. The antiderivative of 1 by root x is 2x to the power of 1 by 2, which is 2 root x. So if you think about it, when we differentiate 2 root x, we obtain 1 by root x. And if we perform anti-differentiation on 1 by root x, we obtain 2 root x. So the algebraic way is to first consider the derivative of x of a root x, which is half times x to the power of minus 1 by 2. Multiply the left-hand side and the right-hand side of the equation by 2, and we get the derivative of 2 root x as x to the power of minus 1 by 2. Now part C. The antiderivative of e to the power of 2x plus 1 is e to the power of 2x plus 1 divided by 2. Remember, e is the natural exponent. So using the algebraic method, a more algebra-based method, consider the derivative of e to the power of 2x plus 1 with respect to x. So that is equal to 2e to the power of 2x plus 1. Divide the left and the right-hand sides of the equation by 2, and we find that d by dx of e to the power of 2x plus 1 divided by 2 is equal to e to the power of 2x plus 1. Thank you guys. That'll be the end of this video. Make sure you hit the like and subscribe buttons to see my future videos on mathematics. Until then, stay tuned.